When an audio source or a sound is going to be converted into a digital signal, I'm going to show you how that process works. The sound waves in the air are always going to be analog, so it starts out as an analog system, and the way we kind of visualize that is sort of a swoopy line. Okay, so I don't know if we need to go over all the little things, but from here to here is the wavelength, and the frequency is based on the wavelength. So when you're going to convert this continuous, this line never breaks. It's every tiny, infinitesimally small point is represented here. It's continuous. So to make it digital, we have to break it up a little bit, and hopefully we'll break it up small enough that it still is recognizable when we have to play it back. So I'm just gonna, I guess I don't need to draw axes, but I think it'll help. So this is time. I don't want to get too mathy for you, but it's important to know that it's not just a picture on the screen. This is moving through time. When it starts, it's in the middle, and then it goes up and down, and it's not. Don't get too caught up with the picture, I guess. So when we're going to digitize it, we have to look at the sampling rate. Sampling rate, and that just means how often we take a measurement of where this line is on the vertical axis, the amplitude or the pressure. This measures a few different things, I guess, but on the vertical axis, the sampling rate is how often we take a sample. So what's a sample? That's like at this first point, we'll call that point 1. Then the measurement is right here at whatever volts. It doesn't matter. This could be volts if we're talking about electrical current. This could be pressure if we're in the speaker, or I wrote amplitude, but whichever thing we're measuring, whichever state we're at, it has this vertical axis and it has time. So we measure, I guess I'll just stick with volts for now. However many volts that is, we write that down, so to speak. And then at the next one, we write that it's a little higher, a little higher. So this is a pretty good sampling rate of this curve, because then if we go to reconstruct it and we have ... we can smooth them out and get the first part of that curve. If we were to just sample every really far apart, I'll just draw a few randomly spaced lines, then we would have this point and then down here. And if I were to try to reconstruct the line just by those, I would get just a big swoop, and that doesn't look right. So we need a high enough sampling rate to fill in all the little spaces and reconstruct the curve the way it's meant to be. I should probably just get rid of this bad line. And how high does the sampling rate have to be for a certain piece of music or a certain sound? That is determined by the Nyquist limit. The Nyquist limit just says, rather simply, it's a simple proof that for a frequency like this, you would have to sample at least twice for each of these things, for each wavelength. Because if you only sampled here and then here and then here, you would get a straight line. If you sampled 3/5 as fast as the wavelength, then you would get weird dots crawling around. But if you sample at half, then you're able to get the top and then the bottom of this one and then the top of this one and the bottom of this one. And if all you have is tops and bottoms, you can still do a decent job of reconstructing the curve. You at least get the major gist of it, the top to bottom ratio. So that's all the Nyquist limit is. It doesn't say a whole lot. If you're trying to record up to, let's say, 16 kilohertz, that's an H, kilohertz, or HZ. Maybe I shouldn't be writing hertz. That looks right. So, K is kilo for 1,000, so 16,000 hertz, and a hertz, to review, is a cycle per second. So I'll rewrite this in a new color. That means 16,000 cycles or oscillations, or top to tops, or bottoms to bottoms, if you want to look at it that way, per second. So if we're trying to sample 16,000 hertz, according to the Nyquist limit, we would need twice as many, because if this is our cycle, if we sampled at 16,000, we would only get this, we'd get a flat line. So we need 32 kilohertz for our sample rate. Okay, I guess we can talk about the bit depth. I think I'll just draw a whole new graph for this. If we have, let me draw a new sine wave. This is up, down, well, good enough. So I'll draw my axes again, they make me feel better. For the bit depth, or I forget the other word for it, but I'll just write bit depth in the digital color of blue. Bit depth. That's how many bits we're using to represent the vertical aspect of this. So if we only have one bit, and this is for each sample that we take. So on this first sample, if we can only use one bit, then we look here and we're trying to write down how high this point is on the volts, or on the amplitude. We're trying to write it down, but we only have one box, and we can only write a 1 or a 0, because that's what a bit is. It's either, there is electricity here or there's not. So if we only have a 1 or a 0 to work with, we have to round it off. So it's, just for simplicity, we'll say that's 1 volt and that's 0 volts. We have to round it to 1. And that means that our, time to use a new color, I guess, that means that our recording is going to be played back all the way up here. And that's not what we want, because then we go to the next point, we're supposed to record here, and we move that up, and we get to here, and we're still rounding up to 1 until we get to here, and then it rounds to 2. I should probably use green for what it actually is, and dark blue for what we end up recording. So then our recording looks like, zap, all the way down to here, and then over, and it kind of looks a little bit like the wave, but it's not very good, so I think I'll just delete that part, and we'll give ourselves another bit to work with. If we have 2 bits, then let me erase the 1. Then if we're sampling yet another color, I'll use red. If we're trying to sample this point, then now we have 2 bits to work with. So we can say this first one represents the halfway point, so that's the halfway point, is this one. And then if it's a quarter, I'm trying to keep track of all my colors, if it's a quarter, then we use the green one. Maybe I'm starting to lose you, but I'll go through pretty carefully and try to explain this. I'll use brown. So if we're trying to record this first point, okay, how are we going to write that up here with only 2 bits? We'll say yes, it reached the halfway point, so 1 represents a yes, it reached the halfway point. And then do we add another half to that? Well, no, because it's not all the way up here yet. It's just at a half, so we write 10 for this point. And then the next one's right here. We would write yes, it reached the halfway point, and yes, it reached another quarter. I'm not sure if my analogy is still holding up perfectly, but you can see that if we add yet another box, then that would give us more in-betweens. We'd be able to have eighths, and then we could say, oh, well, it doesn't quite reach up to this one yet. If we're measuring, I don't know, this point, it doesn't quite reach up to this one. It's a little above that one, so we're still rounding off. And the rounding off is, what is it? Digitizing error, quantizing error. quantizing error. Okay, because you're always going to have to round off a little bit. The lines that you get are never going to be perfectly precise, because analog system, or the analog curve that you get, has infinitely small measurements. So the sampling rate is one measurement of getting better and better reproduction, or better recording. You can fill these in. You can have higher sampling rate to get more dots on the curve, and then the bit depth, or the bit storage, whatever, tells how accurate the dots actually are. Because if you have a really high bit rate, if you're sampling every million, billion, billionth of a second, but your dots aren't following, if they're rounding off too much, then it's not a good recording. And if your dots are right on, as in this example, if your dots are exactly on the curve, but you're only collecting once in a while, you're going to get a really dumb curve too. So both of these things are important, and they're the two main ideas of what you need for digitizing an analog signal. And amplitude and frequency are the two, the x and y axis is what I like to think of it, but maybe you're not a math person. I just want to show that they're both important, and they're pretty distinct from each other. Like, if you have one, it doesn't guarantee a good signal. You need both. So I think that's a good enough review for that subject. See you next time.